Hello, welcome to AP Physics 1, Unit 2 and 3. Today we'll be going over spring forces and energy, which is why it's Unit 2 and 3. So springs are a prominent part of physics tests, and it's good to know more in depth of the mechanics and true workings of a spring. So to start off, there are two types of springs, a Hooke's law spring and a not Hooke's law spring. So let's start off with a Hooke's law spring. This is the most common one, and the forces of these springs are denoted by the equation F equals negative kx. So what is K? K is the spring constant and basically means the strength of the spring. The higher K is, the more force the spring pushes back as you compress it, so it will hold its shape against more force. So now what is X? Well, X is the distance that the spring is pulled or pushed from its regular resting position. So the more X is, the more it's either being compressed or pulled, and therefore the more force that the spring is applying to get back to its resting position. And now the negative in the equation basically just means, since it's the opposite direction of the push, that's why it's a negative. Now a non-Hooke's law spring is basically a spring that doesn't follow this linear relationship of negative kx. Instead, it follows a different line, which most likely is a curve. And this equation of the curve will usually be given to you on the question, and you can use the equation just as you would with a normal spring. So we'll be going over some of those in the practice questions, so don't worry about those. So now that we've covered force, let's cover energy of a spring. Now this is Unit 3 territory, so feel free to skip if you haven't gone to energy yet. If you're taking Physics C right now, you'll know that work equals the integral of force with respect to distance. So taking that logic, the integral of kx, negative kx dx would be negative 1/2 kx squared. So this is our spring energy. For those not taking Physics C, all you have to remember is that 1/2 kx squared is spring energy, and that can be used to calculate when objects hit the spring. Springs are usually energy conservative unless said otherwise, and so we can use this to calculate speeds off the spring, as you'll see in the practice problems. So let's go over some spring practice problems. Okay, so for this first question, we'll be discussing spring forces, so not energy but forces. So the question, you're gonna have to use a little bit of imagination here with the spring that I've clearly written. Let's say that this minecart goes this way, and then it compresses the spring all the way, so all the way down 3 meters. So how much force at that point is the spring exerting onto the minecart? So we use this formula, F equals kx, and since it's just force for now, we don't need to use the negative part. And so we know that spring constant is 2 and there's 3, and so since it goes all the way in, x will equal 3. So that means that the force will equal 2 times 3, which is 6 newtons. And that is the force that the spring exerts onto the minecart. Okay, so we have another more complicated force problem. And this is regarding this string right here, which we will just assume is a spring this time. And so the question is, how far from equilibrium does a spring get stretched? Which is actually the x value. Now it's important to note that the x value does not cover the whole spring. It is just the distance that it gets stretched from the equilibrium. So what are the values we have? The mass of the llama, which is 10 kilograms, gravity, which is 10 meters per second squared, and the spring constant, which is 4. Now we need to solve for x here, so let's first start with the free body diagram. The llama's free body diagram is, it's a bit tilted. If we have the square here, mg goes straight down, and the spring force of spring force goes directly upwards, and we're assuming that the law must stay still, and we're just trying to figure out when the spring is still. So we know that the net force in the y direction equals 0. Therefore, the spring force minus mg equals 0, which means that spring force equals mg. Now, spring force also equals k of x equals mg, and so we can say from that x equals mg divided by k. Now what is that? Well, we know these values right here, so we can just plug it in and say x equals 100 divided by 4, which equals 25. And that is the amount of distance that the spring is being pushed down. Now we have another problem here, and this is an energy problem, so this will involve spring energy. So we have a minecart that's about to roll down this rail and then hit the spring. And when it hits the spring will get compressed by 2 meters, or here, it'll get compressed by 2 meters. So the question is, what is K of the spring? Now we know that the mass of the minecart is 10 kilograms, and the gravity is 10 meters per second squared, and the height of the minecart where it starts is 4. So for the energy problem, and it's also frictionless, so that means that energy is conserved. So we can say that mgh equals 1/2 mv squared due to E1, the mechanical energy being conserved. We can say E1 equals E2, and we can say after, when it's at this is the phase where it's at 1/2 mv squared, we can say once the minecart stops, how far in is the spring? Well, the spring is at max energy at that point, so we know that it's like this. Once the velocity becomes 0, then the spring, since at this point it's 1/2 m0, we can cross that out and say that 1/2 kx squared is now all of the energy. But we will notice that these two are the same, right? Since energy is conserved, the speed that the minecart leaves the track is also going to be the same speed that the minecart enters the spring. So we actually don't even need 1/2 mv squared, and we can just say that these two are equal to each other. So mgh equals 1/2 kx squared. So we know m, we know g, we know h, and we know x. So we just need to figure out what k is. So we can just use algebra. 2 mgh divided by x squared equals k. And so once we plug those numbers in, we get, from that we know k is 200 newtons over meters, which is actually the units that you have to use for spring constant. And so this, what we know from this is that it's a very high number, and it means that the spring is very, very resistant to a lot of force, which makes sense. And so that's all the spring questions. Thank you for watching.